What is this loop? The loop, every time, take how many bytes? Let's say I have 1,000 bytes in the buffer. Every time, it processes how many bytes? 2 bytes. Right? Because it's unsigned short. Unsigned short. And why we know that if every time it processes 2 bytes, now it depends on how good you are writing in C here. Wow, complicated, huh? So basically it's W++, okay? Have the return value and then increment by 1, okay? So why I say that it depends on how good you are writing in C. So what is the meaning of I have an unsigned short pointer and then plus 1? It will move forward 1 byte or 2 bytes. 2 bytes. Okay, it depends on data type. Okay, so that means that every time you dereference a pointer, dereference it, and add the value that you're currently pointing to an accumulator called sum. Every time you take 2 bytes and move forward by 2 bytes, and that's why you are exhausting the data inside the buffer every 2 bytes. Okay? And what is the main characteristic of this checksum algorithm is using plus addition. It's the addition to do the checksum. Very interesting why addition is useful. Later on you will see it. Okay, so that means that every 2 bytes add with every 2 bytes. And what's next? It will also count how many bytes left. After it's run off all the bytes, then it will quit the loop. It depends on how many bytes you have, odd number or even number. If it's odd number, because we're doing the processing 2 by 2, so there's a problem with remaining 1 byte. Don't miss him. Don't miss him. We will take into account how to process this. Okay, so just pull it out. Okay, pull the 1 byte out, and then add it. Not add it. I mean, make it into a storage called answer, and add the answer to the sum. Okay, so maybe let's take into account that the odd number we ignore it first. Let's consider even number, so we can skip the green block. Now, what is the orange block? Orange block is interesting, very interesting. What is it? I only say that reduce a 32-bit number to a 16-bit number. Okay, so what is that? The sum, what is the data type? Data type, what is the sum? Integer. How many bytes for integer? 4 bytes. No matter what architecture you use it. 4 bytes. So that means that there is the accumulator is big, and you may have a very long buffer. Then the accumulated value may get beyond 16 bytes, 16 bits. I mean, okay. So even though you every time 16 bits plus 16 bits, eventually you will use 17, 18, 19 bits. So we need a storage that is big enough. So it's 4 bytes. Okay. But what is the requirement of this checksum algorithm? I never said it before, right? The requirement of this checksum algorithm, it only wants 16 bits of output. So what should you do? Okay, so you have some extra bits that you don't want, and they have a very clever idea. The clever idea is pull out the most significant 2 bytes and the least significant 2 bytes. One is using bit shifting. One is using bit mask. Okay, so this is called bit mask. Okay, so what does the bit mask means? What is 4F? 4F, how many bits are there? 4F, how many bits? 16. Okay, so let's imagine that this number, I use it as a 4 bytes integer. 4 bytes integer, but I also say that this number only take up 16 bits. Okay, so what does this look like? The first bit, okay, the least of bits up to the 16 bits are all ones. Beyond that, 17, 18, 19, up to 32, all zeros. Okay? And that means what? That means I use this bigger number. I don't know how large it is. Maybe it's already consumed up to 37 bits. Okay, no problem. When I apply this bit mask, what are left? Only the last 16 bits left. The higher bits, gone. Okay, so I finished half of it. How about here? Another half. So what is it? How many of you don't know about this operation? How many? What is it? Bit shift. How about you? Do you know it? This bit shift. So what's the meaning of bit shift? 0, 1 become apply bit shift of 1 bit. 0. 1, 0. Shift by 1 bit. 1. Okay. So remember, after you shift, you will feel 0 on your right. Okay. Yeah, I sometimes I mix up left and right. Okay. So that means what? That means what I'm doing is I'm sacrificing the least significant 16 bits. I remove them all, shift it out, go away. And what's left is the most significant 16 bits. Okay? And now it becomes two 16 bits data add together. Okay? And why we keep this into the sum variable but not the answer variable? So what is the answer variable? What is the answer variable? Answer variable is 16 bits. Answer variable is 16 bits. Now I already know that after this operation, I take the least 16 plus the higher 16, add together. Why we don't use the 16-bit storage to store this answer, but still use the sum variable? And you know I always make a PowerPoint wrong, right? Is it my bug? Where? I hear. Yeah.
It may be a 17.
Maybe there is 17 bits. So, anybody get his idea? So let's say that I have a two digits number. Is it possible that two digits number? So if it's from 10 to 99, right? From 10 to 99, add to another from 10 to 99. Will I produce a third digit? Yes. It's possible. So this is here is still possible that after I do this transformation, I still get a number bigger than 16 bits. So I need to take this, save it into a 32-bit storage, not the end of the game. The end of the game is, I know that it happens, that it will go overflow, go to the 17 bits. No problem. Last sentence here. If it go over, I will use this to pull it out and add one more time. Okay? Done. It is done. Okay? And last is just do a bitwise knot. Okay? Just a bitwise knot, so you can say that it's not necessary. Okay? No problem. You can just consider it does not exist, but in the code it really exists. I read from some document. It tell me that it is because it is doing once complements addition. Okay, so by the end it's not all the bits. Okay, do you still remember this from ENGG 2020? Yeah, I already forget it. Okay, I take it more than 15 years ago. Yeah. What is that? I can't remember. Okay, so yeah. So what is it about? This algorithm is very interesting. How interesting it is? It keeps on accumulating data 2 bytes by 2 bytes. And how can I guarantee it that, I should say it again. How can I create 2 byte streams so that I will generate 2 different byte streams, generate the same checksum? Now the problem becomes very interesting. Let's say I have this 4 bytes. Let me use a Sublime to type it. Okay, so let's say I have a bytes number 1, 2, 3, 4. This byte stream. Okay, A is a byte, B is byte, C is byte, D is byte. I use this 4 byte to generate checksum. Okay, and using that algorithm. Can you construct another byte stream? X, okay? Oh, sorry, it's X. Okay, E, F, G, H. Okay, so that E, F, G, H. Okay, should equal to A, B, C, D. I don't know what is the position. Okay, can you just flip the ABCD so that the two different byte streams generate the same checksum? 4 bytes. And take a look back into this algorithm. By the way, did I start the recording? Should be right. Yeah. Forget about it. 4 bytes. A, B, C, D. Okay, they give you a byte streams that construct the same results, but they're different. Then you will know how powerful this checksum algorithm is. Or what is its strength, I would say. It's not powerful, but it has a strength. No, this one? That's it. RDT CDAB. Let me write it down. Okay. So M said that is CDAB. Any other answer? At least you can find one more. Yeah, this is the correct answer, okay? Correct, okay. One more. Huh? Oh, okay. What is that? Beep, 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 beep. Huh? One by one. What is the answer? CBAD. Is it? Good. Correct. Any other ideas? What? C what? A B C D? Huh? A D CB. Okay, yeah, I shouldn't say A B C D. Next time it's 1, 2, 3, 4. Okay. Any other idea? Any other options? Should be no, guys. A. Yeah, should be. All right. Is there one? Yeah. So those people who know how to answer already fully understand this algorithm. The algorithm core, what is the core of this algorithm? It's this operator. This operator is a core. And data type unsigned short is also the core. Okay? So it's always processed 2 bytes by 2 bytes. Now look at here, why they can know that this is correct answer. Okay, so basically AB will be going to add to CD. Okay, so look at here. Are they the same? Yes, they're the same. If you consider it as an addition operation. Now how about this? The next guy. Next two guys, are they the same? B to D, A to C, just like the first byte stream. Okay? So they are all look the same and will produce the same results if we understand that it's processed the data stream 2 bytes by 2 bytes. Okay? Now what is the problem here? The problem here, look at here. If we want to generate a byte stream, a bit-stream byte stream, and we want to attack this algorithm and say that this algorithm is useless, what we want to achieve is to flip the bytes, right? Not flipping the bits. Not changing something within the bits, okay? Because you change something within the bits, okay, you need to cooperate your partner. Maybe you're flipping this guy, okay, to A prime. Then your partner will be C prime. Or even more complex, you use your carry or something like that. I don't know how you do it, okay? But the easiest way to think about it is you flip the bits in A and you want to attack this algorithm to generate the same output, same checksum value, then you have to cooperate not the next byte, but the bytes after the next. Is it possible that we can generate such a strange behavior, very, very seldom, very rare, probability is very low. Okay? So the strength of this algorithm is not to give you a cryptographic checksum. That means that not guarantee that I give you different byte stream, I give you different checksum. No. It just try to tolerate bit flip, change of the bits. Okay, not flipping the bytes. And this is the strength about this algorithm. Okay, now these are the questions that I used to ask during the final exam. Okay, yeah. How about I change the core of this algorithm? The core of this algorithm, I said it is this operation. I change this plus equal to become bitwise and equal. Is it useful? Is it still a useful checksum algorithm? Oh, by the way, how to define what is useful? Okay, let me define how to define is useful. It should be deterministic, right? Deterministic is always deterministic. Is it become bitwise and? Yeah, it don't give you randomized result. Then it is deterministic. Good. Can it generate checksum that we can detect one bit error? Or I should say, what is the probability that we have a two different data stream and they produce the same value? Is the probability high or low? If I change the core, become bitwise and. Two different data streams. Will it generate the same outcome? Yes, why?
They will almost certainly be zero.
Mm-hmm. And as I say, it must be zero. Look at the initialization value of sum.
Oh.
It's zero. Okay? It's always zero. Okay? This algorithm will generate always zero. It's useless. Useless, totally useless. No matter what is the stream, it will always report sum is zero. And sum is zero, then consider it the transformation in the orange blocks. Then eventually answer will become all 1 because of the bitwise not. Bitwise not. Okay. Now I give you another variation, bitwise OR. Is it useful? Bitwise OR. Yeah, some already say no. You say no. So how many of you also say no? You say no. Not useful. How many of you think that it's useful? Bitwise OR. Yeah, OR. Yeah. Okay. So bitwise OR, what will be the outcome? Very probably 1. All 1. Okay? Once the bit becomes 1, it will never become 0 again. Okay? So give you one more, that's hard. Exclusive OR. Bitwise exclusive OR. Is it useful? Yeah, this is testing your knowledge over ENGG 2020. Actually, do you know that exclusive OR can be changed in? Not changed. It's helpful in calculating addition. Yeah, some already say that yes. Okay. Yeah, I know this is beyond this course scope. Okay, but 2020 you must have taken it. Okay, the one who teach you should be telling you that exclusive OR can help you to implement addition. Okay. Only what is missing is carry. Okay, it's very similar to doing addition. Okay, so I will say that it is useful. It's useful in the sense that it generates different outcomes, but it's become hard to predict what will be the. I give you the stream, okay, ABCD. You immediately can tell me that what is the colliding by streams, but if it is an exclusive OR, it's very hard to determine. Okay. So I will say this is kind of useful, okay? So this is some variation here, but I looked through all kind of systems. We are using this algorithm, okay? This algorithm is already documented in RFC, okay? So cool, not cool, okay? Only a simple algorithm, okay? I need to talk about this algorithm because in assignment 2 you will be using it, okay? Although our tutor will give you the code, okay? But you know how to use it. Okay, so this is just some simple calculations. Okay, And then this is the design of the UDP header. I never said anything about UDP header, right? The UDP header is exceptionally simple. How simple it is? Just a few things. Source port, destination port, the checksum for the entire thing together with the header and the body. Body means an application layer message. Okay, and what is the segment length? Segment length is the length header plus application. Okay, so later you will use it in assignment 2. Assignment 2 is you are actually implementing a protocol analyzer. You analyze the protocol and know that, oh, this is protocol UDP, and UDP how to extract the useful field and how to modify some of the fields. Okay, assignment 1 is the application layer. Okay, so why using UDP? I will say that just overhead. The overhead is small. Mark Zuckerberg also tell you that about the overhead. If it is, too many people going to queue you, okay, you need to maintain too many connections and using many of the RAMs. Okay, so I will say that this is also one of the implementation consideration for the DNS protocol. Okay, DNS protocol, you expect that like a Google 8.8.8.8, they are public DNS. I guess every seconds, millions of queries will be sending to him. Oh, I know, I don't know the server's him or her, okay, but him. Then it will take many memories if it is TCP, okay? So of course the things change, okay? What does the things change? People already are not like DNS, okay? They propose a secure DNS, okay? Some secure DNS, and they even try to not using UDP anymore, okay? But this is out of scope of the transport layer protocol, okay? And everything is about overhead, but what is sacrificing is the reliability, okay? So the principle now, I guess I should stop today after two few slides, okay? What I'm going to teach you is some fake protocol. The fake protocol can motivate you how to think of the real implementation of TCP. Okay, so what is the meaning of motivation? I will assume like this. Illustration, or not illustration, illusion, okay? Illustration is here, illusion is here. The illusion of having a TCP is like you have a reliable data channel between two applications, and these two applications may be running on different machines. And this is illusion. And what is the illustration here? The illustration here is actually the underlying channel is always unreliable. Maybe it is an optical fiber. I don't know why there's a shark eating the optical fiber. Okay, so generate some error. Okay, yeah. Eating is not being broken yet. Okay, generate error. I don't know why. Okay, is this tasty or not? Okay, then what will happen here? You will generate errors, maybe packet loss, maybe packet corruption. Now we know how to detect packet corruption. But in UDP how to handle packet corruption? Detection is handling is different things, right? I detect it, but I don't handle it. There's one kind of management, and this is UDP. UDP detect it. I know it's corrupted. Goodbye. Drop it. Okay. So what should you do in a reliable data transfer if it is corrupted? Of course, I need to compensate for the loss. Okay, I want to compensate for it. Now, how to tell the other side that it is corrupted data? Okay, of course, by sending a reply. And TCP is about implementing a big finite state machines in both sender and receiver. Okay, so we have a finite state machine for sender side. We have a finite state machine for the receiver side. And this is a very, very simplified scenario. The real scenario is the same application underlying in the transport layer protocol. You can be a sender at the same time you can be a receiver, right? Because we go through a socket, you can call read system call, you can call write system call. So you can be reader, you can be sender at the same time. So that means the two finite state machine will be integrated in one side. So this is a simplified scenario already. Always going from here to here. And when you look at later slides, okay, yeah, I can go fast forward a bit. Yeah, fast forward a bit. Look at it. Wow, what's that? Wow, what's that? Okay, so it is the financing machines in implementing simple yet useful, reliable data transfer algorithm. Okay, and I usually name this the ping pong algorithm. Okay, what does it mean? Just like playing ping pong. Okay, you start the game. Okay, you fire a ball to the other side. The other side will give you the ball. Okay, but in networking, that ball is no longer the same ball. Okay, just one ball keep firing. Okay, and we call it reliable data transfer protocol. And then later we will talk about one famous protocol called sliding window protocol. And the sliding window protocol is to enable firing many balls. Okay, now think about it in a ping pong game, many balls flying around. Okay, we call it pipeline. Pipeline. How to pipeline so many balls flying around without problems. Okay, or you can detect even one ball is lost. Okay, we call it sliding window protocol. And then we will go into the real TCP implementation and see how TCP will achieve all the things that we talk about. Okay, and this will be boring part of this course, most boring part of this course, because what? I cannot tell you to write the program. Okay, or I cannot show you codes. Okay, because all the codes become a C code inside the kernel. Okay, I mean, I kind of try to understand it, but I fail. Very hard to understand.